Okay, hello everyone. Welcome to another episode of Science and Technology History Q&A. So I'm supposedly on some kind of vacation, which means I'm not where I usually am. And I thought I would be able to have some lovely, interesting, natural backdrop, but turns out that doesn't really work technically. So it's kind of things will look boring, unfortunately. And I'm on an island called Nantucket, which last weekend was about to get a hurricane that didn't arrive. And now it's unbelievably hot and I'm having some weird allergy. So that's what happens when one is supposedly on vacation. What vacation for me means is a slightly lower density of meetings, and I choose for myself to work on various projects that I hadn't gotten to at any other time, including have a big pile of books to read, which so far I haven't managed to make much progress on. Somehow I think that Kant's Critique of Pure Reason, which is one of the books I have with me, that I'm meaning to really dig into, because I think now that I've really thought about a lot of these issues, I have a better chance to understand it. And I want to understand the kind of historical connections of what I'm doing to what Kant said. I was considering it, not that I really do beach reading, but I was considering it as a kind of a somewhat unexpected type of beach reading, but we'll see. All right, well, let's see. We have a number of questions here, so let me see what I can do here. It's always fun to see what comes up here. This is always my micro vacation for the week. So now it's a micro vacation within a vacation of some kind. All right, there was a question here from IC about the history of computer algebra systems. Okay, so what is a computer algebra system? It's a thing that I've used for a large fraction of my life and have built sort of the main version of in the world these days. It's a system for doing algebraic computation, for taking algebraic expressions like, I don't know, x to the fourth minus 1 or something, and algebraically turning that into whatever that factors into, x squared plus whatever it is. So the question is, when did people think about doing that? Well, I have to say, from the very earliest days of people even talking about computers, people kind of thought that you'd be able to do things like that. I'm not sure if Leibniz, who had this idea of a kind of a computer for crunching kind of logical expressions that could represent things like legal questions and things like this. He certainly did quite a bit of algebra, and in his work on inventing calculus, he was sort of led to do lots of algebraic computation. I've looked at a bunch of the calculations he actually did. He was okay at doing algebra. He was pretty terrible at doing arithmetic. And you can see lots of random mistakes he made in doing long multiplications and so on in the papers of his that are preserved. In any case, I don't think that, even though he was interested in constructing physical computational devices, like he constructed out of brass a kind of 4-function calculator, arithmetic calculator, I don't think he had the idea of doing algebra on that, but I'm not certain. But certainly by the time Babbage in the 1830s, 1840s was thinking about his analytical engine, his kind of mechanical device that could be programmed to do various kinds of arithmetic and other operations. By the time that was being thought about, in fact, in his own work on the analytical engine, I don't think Babbage came close to thinking about doing algebra, so to speak. He was really thinking about his analytical engine as a machine for generating arbitrary kinds of mathematical tables. So there might be one mathematical table that was for sines and cosines, another one that was for, I don't know, Goodamanians, just to give an exotic example. Those are the functions that people don't use very much right now, but they were introduced by a student of Gauss's, actually. And they're kind of the thing that converts from trigonometric to hyperbolic functions. That's sort of an aside, but I'm just saying different kinds of things one might compute on Babbage's concept of the analytical engine were sort of things that were various kinds of mathematical tables. Now, Ada Lovelace, who kind of wrote this exposition of the analytical engine, I think understood much more deeply than Charles Babbage did, sort of what the thing would be good for. And I think really understood much more clearly this idea of what we now would call universal computation. And she has this lovely comment where she says, because the analytical engine will be programmed, it was never built. A sort of junior version of it, the difference engine, which just does interpolations of mathematical functions and computation of polynomials, that was built, but the analytical engine was never built. That's a long and different historical story about how that didn't get built and the various missteps that caused it not to be built. In any case, it wasn't built. But Ada Lovelace wrote sort of an exposition about the kind of the concept of the analytical engine and the way the analytical engine would work if it were built, so to speak. And by the way, if it had been built, it would have been the size of a giant steam locomotive type thing made of gears and so on, crunching away, doing computations. But it was programmed using punch cards. Punch cards were invented like in 1800 or so by Jacquard in connection with the Jacquard loom for weaving, for specifying patterns of weaving to make. And so Ada Lovelace has this nice comment where she says the analytical engine will weave algebraical patterns much as the Jacquard loom weaves patterns of pictures of birds and flowers. And she had a reasonably general notion of what algebraical patterns might mean. And I think that included the concept, I think, of doing algebraic symbolic computations. See, one thing is to say, I've got a polynomial, x squared minus 2x plus 7 or something, evaluate that for a particular numerical value of x. Another thing is to say, take that as a piece of algebra and do transformations on that thing as a piece of algebra. It's kind of a higher level of abstraction above kind of just the evaluate the algebraic expression. I mean, in a sense, that's the very invention of algebra back in the 1400s by Vieta and people like that, was this notion of you can do operations algebraically. You can say, I can turn x squared minus 1 into x plus 1 times x minus 1. It doesn't matter what x is. X is just a symbolic variable, and that transformation is always correct. And that's kind of an essential idea of algebra, sort of transformations that are true for all possible, let's say, numerical values of variables like x. But so then the question is, when do you get to figure out that you can do these pieces of algebra, which humans have been doing since the 1400s? How could you do those? Could you think about doing those sort of automatically by machine? And I don't know if, I don't think Alan Turing particularly talked about that, nor did John von Neumann, I think, in the early days of computers. I think much more was this idea of you've got a sort of a first level mathematical expression, and you're going to evaluate it, or you're going to compute, let's say, the digits of pi or something, rather than that you're going to produce, let's say, transform a symbolic expression or produce a series of symbolic expressions. Now, it certainly was the case that things were, people had the idea that you could represent, let's say, polynomials as lists of coefficients, and then you could be generating, which polynomials satisfy certain conditions. For example, in the 1950s, for sure, people working out things like shift register sequences were doing things where you took the sequence of values of coefficients in a polynomial and you're doing operations on that. Like when you multiply polynomials, you take the two lists of coefficients and you do this sort of convolution operation between these two lists of coefficients. But in a sense, nobody was writing out the polynomial as a thing with x's and so on in it. It was all like, let's turn this into sort of an array of numbers and then we can operate on it with a computer. So I think that the earliest examples of computer algebra as such, well, there are a number of different pieces. There was a thing called Altran that was developed at Bell Labs, I think in the early 60s. It was written in Fortran, and it was sort of an algebraic Fortran. By the way, confusingly enough, Fortran itself, the very name means formula translation. And in the early days of computer languages like Fortran, they were sometimes referred to as algebraic languages. Why? because the idea was that you could take an algebraic expression like x squared minus 1, and you could fairly directly write that as a piece of Fortran code. Before that, the only way to specify the operation x squared minus 1 was to say something like, take a value, load it in a register, take the value, copy it to another register, multiply the two registers together, subtract 1. You weren't doing something where you had a formula like Fortran, the formula translation system. It wasn't something where you had a formula, something sort of algebraic that you could actually look at in sort of human mathematical terms, and it would be automatically, with a compiler, turned into something in the machine code of the computer that could be executed by the computer. So that was kind of an idea from the late 1950s of things like Fortran, the idea that one could translate from an algebraic form to the actual instructions, the machine code of the computer. So somewhat confusingly, you'll see references to sort of algebraic languages, by which they mean you can take an algebraic expression and turn it into machine code. That's very different from taking the algebraic expression and actually manipulating it as a piece of algebra to get another algebraic expression. So I think the earliest time that I know of a very serious effort in algebraic computation sort of initiated around 1962, and kind of the idea, I should explain another part. When people were interested in kind of, back from when people thought about mathematical logic in the 1930s, people like Gödel and Church and so on, talking about mathematical logic, the idea arose that you could have a logical expression, a symbolic expression that was ands and ors and predicates of other kinds and some function, maybe a function f where you didn't know what that function f was, all those kinds of things. You could have expressions that were symbolic. And you could think of what later became known as the process of computation as being a bunch of transformations between those symbolic expressions. And so, for example, lambda calculus, invented by Alonzo Church around 1935, that kind of very much has the idea of a lambda expression is this thing that is sort of, in some sense, when you see them written out in kind of papers and so on, they have an algebraic notation, although their variables, x, aren't, in standard algebra, we say x squared minus 1. Okay, what do we mean by x? We might mean where x is any number, but we don't really specify sort of what you do with the x. In lambda calculus, we say lambda of x, x squared minus 1, and that means this is the thing which is going to act like a pure function, and when you feed it something, it will consume it, bind that to x, and evaluate x squared minus 1, or substitute x for x, whatever you feed it. But in any case, so the idea of sort of symbolic expressions was something that existed in lambda calculus, and it was something that had been investigated kind of as a matter of sort of the theory of mathematical logic, transformations between those expressions, lots of stuff. You could even think of combinators, which are a more primitive form, a more deeply machine code version of that kind of thing. They've been invented in 1920, although were not widely understood, but were used as sort of the backstop of various theorems about lambda calculus and things like this. Anyway, so those things all existed. And when people started thinking about artificial intelligence, one of the ideas was, well, brains must do things symbolically too. Let's use kind of this mathematical logic tradition of symbolic expressions and use that to do brain-like things. So one person who did that particularly was John McCarthy around 1958, developing Lisp. And I think, I don't know, I never had a chance to talk to him specifically about this. Other people have claimed that his sort of knowledge of lambda calculus was a bit wonky, but in any case, he definitely used sort of the idea of transformations for symbolic expressions in the construction and conception of Lisp. Although Lisp wasn't really implemented seriously at that time, that was kind of a thing that was out there as a thing that would be sort of transformations of symbolic expressions, just as lambda calculus had done that. And whether that could be used for mathematical transformations of symbolic expressions wasn't particularly clear, although I think McCarthy may have given some examples of mathematical transformations like that. Okay, so roll time forward a few years, 1962, one of the things that, one of the big use cases for complicated algebra is physics, and in particular, particle physics and the evaluation of Feynman diagrams. So Feynman diagrams are this way of representing diagrammatically complicated mathematical expressions that represent things about the probability of particles scattering in theories like quantum electrodynamics and so on. So there were these, and what you do is you work out sort of the biggest effect is the simplest diagram, and then there are smaller and smaller scale effects that correspond to more and more complicated diagrams. And these diagrams involve more and more integrals and more algebraic complexity to work out. And Dick Feynman certainly used to believe that it was crazy that you needed to use all these Feynman diagrams to work out the results of quantum electrodynamics. And we're vaguely beginning to start to see perhaps ways to work out those results without going through Feynman diagrams now. And in fact, our new sort of fundamental theory of physics gives one a new direction for working those kinds of things out. But nevertheless, back in the day, around 1960 or so, that was kind of the bane of doing lots of kinds of particle physics, was just working out all these Feynman diagrams. At that time, it wasn't yet known. Quantum electrodynamics had been quite successful. It wasn't QCD, quantum chromodynamics, other kinds of theories where Feynman diagrams are really relevant weren't yet in their heyday. That wouldn't happen until the 1970s, till the mid-1970s. But anyway, there was a certain group of people in the 1960s who were trying to do things with Feynman diagrams for example, quantum electrodynamics, and just running into these absurdly complicated algebraic operations that had to be done. So in 1962, there were 3 people who were interested in that, who all met at CERN, the European Center for Nuclear Research, big particle physics place in Geneva, well, it's across the border between Geneva and France. Those people were a person called Tini Veltman, a person called Mike Levine, and a person called Tony Hearn. In this sort of one meeting, and I kind of tracked this down because I was writing an obituary for Tini Veltman last year or so ago. And so I kind of tracked down and sort of nailed down pretty much exactly, on what terrace at the CERN cafeteria did the actual discussion take place, where people said, yeah, we should use a computer to do all these complicated algebraic calculations that were needed for Feynman diagram evaluation. But anyway, all 3 of those guys went off and started thinking about how they would do this. And at the time, there were different sort of implementation paths. Mike Levine picked Fortran, wrote a program called Ashmedai. Tony Hearn was kind of in the John McCarthy orbit at Stanford and used Lisp. And Tini Veltman was a Dutch fellow who actually had been visiting California at the time when he was doing some of this, decided to use, he decided speed is the most important thing. He'll write his system in the assembly language of what was then sort of the fastest scientific computer, the CDC 6000 series computer. So off he did that. And I've told this story a number of times of saying, if you pick these 3 people and they're all physicists who all do computational things, and one picks Fortran, one picks Lisp, one picks machine code, which of these people do you think later won the Nobel Prize for physics? And of course, it was the person who picked machine code, which is the least sort of theoretically sort of upscale thing to pick. And those 2 things were only tenuously related, so to speak. But anyway, so, and Tini Veltman, it's the only system that I know of where the mnemonics are in Dutch, and where the whole thing is like definitely high on the user hostility curve. Nevertheless, it was for many years the fastest system for doing very large scale algebraic computation. It was used in a number of important calculations about the anomalous magnetic moment of the electron and things like this. But in any case, so at that time, those people went off and built their systems. I would say that the two that did the best probably were Reduce, written by Tony Hearn in Lisp, and Schoonship or Hoonschip or something, can't do the Dutch accent, written by Tine Veltman in CDC 6000 assembly language. Were these things particularly popular? No. Were they used by a circle of people much larger than their creators? Not really. It was kind of student-to-student transmission, I think, at the time, pretty much, in terms of the use of these things. So then, okay, there's another branch to this whole thing, which was kind of the AI branch. And the AI branch led to the MIT AI Lab, and people like Marvin Minsky particularly. And kind of the idea was, this was in the early 60s, people were saying, how will we know when computers are really smart? How will we know that AI has succeeded? Well, maybe it'll be a self-driving car. People didn't particularly talk about that yet. Then people said, oh, it'll be a chess champion. Oh, it'll be able to do autonomous control and walk around as a biped and things like this. And there was one other one, which was it'll be able to do symbolic integration. It'll be able to do integrals the kind of way that freshmen at MIT do integrals and so on, which was felt at the time to be a very human kind of activity, where it's like you had to figure things out and make inferences and deduce this and that to work out the integrals. So that became kind of a holy grail of sort of AI-like things of, we'll know we succeeded when we can do symbolic integrals. So that started a project, I think it was called MATHLAB, was the original name of the project, I think, that was an effort to eventually do things like symbolic integrals. And that was an MIT effort, and that was very much done in Lisp. And it had a bunch of kind of pieces, including things like, oh, let's be able to hand write formulas with some kind of a tablet and optical recognition and so on, a lot of things which are really a bit off topic, but would be very cool if they worked. So that began a project that ended up with a system called MACSYMA, which was a system that was built in Lisp. It was built, and one of the things, the name MACSYMA was something that was kind of a play on this thing, the Project Mac, which was the multiple access computer, aka a time-shared computer. And not only was it a time-shared computer, it was also a computer that was on the ARPANET, the forerunner of the internet. It was node number 236 on the ARPANET. And I think it must have gone online, I don't know when, 1974, 1975 maybe. I know it because I started using it in 1976 as a thing that you could just connect to on the ARPANET and start using the system that had sort of an interactive operating system that allowed you to access things like particularly MACSYMA. So MACSYMA was sort of the outgrowth of the let's try and do symbolic integration. And indeed, there was a program, I think it was called SIN, the symbolic integrator. I think that was sort of a pun of I don't know what, that was sort of the yes, we can do some symbolic integrals now. I mean, it had a number of very human characteristics. Like, for example, one of the ones I think was that it said, in its early versions, before I used it, it said at some point when it was trying to do the integral and it was having a hard time, it said, give me a cookie. And you would have to type in a cookie, and then it would go on and do its work. This was kind of a cute, let's make it more like a human intelligence, so to speak. Some people say, although I don't think that's the only origin, that that's the origin of the cookie concept for web browsers. I think there may be some other claimed origin as well. In any case, the other thing that would happen with MACSYMA is it would do a lot of asking the user things like, is a squared minus, b squared minus 4ac, is it positive, negative, or zero? And you have to answer that before it would go on. And it turned out the answer that you got for the calculation didn't actually care about the answer to that question. There was a kind of an interesting language design glitch there. And of course, when you try to put that into a program, it was disastrous because it would be asking questions all the time. And there's no human, the tree fell in the forest. There's no human to go and answer the question, so to speak. In any case, so that was kind of at the time. So the first system of this type that I used was Reduce. Reduce was sort of existed on some mainframe, IBM mainframe computers. I used Reduce. I then used Ashmedai. And in different places, different people had copies of these programs and so on. And for some reason, I was, I guess, was prepared to do enough kind of hard hat work that I could actually use these things, even though, yes, they did need a certain amount of babysitting and a certain amount of kind of, understanding all the weird things that would happen in weird kinds of error conditions and weird kinds of different issues with preparing data and so on. But that was kind of the notion of. So I started using these things. I mean, I suppose my own contribution to this whole area came pretty much. The key moment was in 1979. I had been a big user of all these systems, and in fact, I think I've become the world's largest user of things like MACSYMA for doing physics calculations and so on. And I built a bunch of stuff on top of particularly MACSYMA, but also a little bit some of these other systems for doing the specific kinds of calculations needed in physics. So, but the system was kind of crumbling under the things that I was trying to compute. And so I was very much in the, okay, what next? And so I, was interacting with the people who built these systems, and it's like, well, maybe you should build version 2 of these systems. And they were like, well, the characteristic thing was the older people would say, oh yeah, well, undoubtedly it could be done better, but we're too old and tired and we're not up for doing that right now. And the younger people, it's always the case, the next generation just builds on, as a given, on the foundations from before. We're like, this is the best thing that ever be built. You're crazy if you think you can build something that will be better than this. So anyway, in late 1979, I started building this thing called SMP. I decided not to use Lisp because Lisp was at that time a quite impractical language to actually run on computers. There weren't good even interpreters, let alone compilers for it. And it was very incompletely implemented in many ways. And so I decided to use C, which was at the time a kind of newfangled language, and built a bunch of wrappers around C to make sort of a slightly generalized C that was a good implementation language for SMP. Needless to say, made many mistakes in the implementation of SMP, but it was nevertheless that system came into existence, first started to be used by people around 1981. I think John McCarthy never really forgave me for not writing SMP in Lisp. And I think he saw that as a kind of a black mark for Lisp in terms of its sort of utility for real symbolic computation. And at the time, had it been, I don't know, well, I'm not even sure today that would be a good choice. I mean, I think that one of the things about Lisp is that it is fundamentally based on the idea of functions, and it's fundamentally based on essentially Church's idea of define a function and it eats things. What I did with SMP and have done with Wolfram language and with Mathematica, it's a different idea. It's an idea of you have a symbolic expression, you have patterns that represent classes of symbolic expressions in which you basically replaced some specific thing, which could be an X and a Y, with something like X blank that represents any expression. You've built these patterns that represent any expression with a certain structure, and then you say, here's how we're going to transform an expression with that structure into an expression with another structure. And that was the basis for SMP. I'm pretty glad that I came up with that idea. In a sense, that idea has roots that go back to like 1920 and the idea of combinators and some of the work that's been done in mathematical logic. I'm actually sort of glad I didn't know some of the things I know today, because today I know some of the very complicated issues to do with the multiple paths of computation that exist in these transformation rules. at the time, I was like, let's just use the first path that works. And that's what we did. And for 40 years, that's been a very successful approach. If you want to understand, and it turns out the sort of the multiple paths thing is very relevant to our fundamental theory of physics and to quantum mechanics and so on. And that's now sort of forced me to understand that more clearly. And I think there's actually a pretty dramatic thing that one realizes, sort of a new paradigm for making theories in science that actually makes serious use of that kind of multi-way, multi-computational process. But that's a story for another day. But back to sort of the history of computer algebra. After, SMP became quite widely used, although it was running on these mini computers that were sort of $250,000 objects and so on. So that limited somewhat its usage. Then when Mathematica came out in June of 1988, I think that was really the time when computer algebra became seriously used by a decent spectrum of people, and where your average theoretical physicist with their own fingers thought they could use it. That was something that I think was greatly helped by the book that I wrote about Mathematica, which I think was quite, I hope, quite readable and quite widely read. I mean, there have been other efforts to do computer algebra kinds of things, the sort of smaller systems. There was a thing called MuMath that was licensed by Microsoft rather disastrously, which gave Microsoft and Bill Gates in particular, I think, a kind of bad taste about things like that for many years afterwards. But that eventually wound up being a system used by TI calculators and so on. But it's this, I would say that the main strand of what became sort of modern computer algebra is pretty much we were responsible for it. I mean, there were things that happened. SMP, for example, I first sort of announced it to the computer algebra community in, when was it? I think it was June of 1981. And that was when there was a group from Canada that started writing a thing called Maple. That they were there, and they were sort of, I think, inspired by this. Yes, you can actually build one of these things from scratch at that meeting in 1981 and somewhere in Utah, where we kind of announced SMP. And then there've been the thing that's sort of interesting. Well, okay, so then there's a question of the algorithmic progress in computer algebra. Just to say a few things about that, like the problem of symbolic integration. When you do a symbolic integral, well, one thing, when I used to do symbolic integrals for doing physics, and I would do them sorted by hand and sorted by computer, the key thing you need to know in doing a symbolic integral is roughly what can the result of the integral look like. Once you know that, and you festoon it with parameters, you just differentiate that general form and try and match it up with the integrand. That's a very good strategy for doing symbolic integrals. It's not one that people would usually learn as a matter of, oh, this is how you do an integral. They learn tricks which are supposed to be easier for humans. The thing I just described is sort of an industrial technique for doing integrals. And actually it gets even more industrial, although I didn't know that in the early days of doing this stuff. Well, in the main strand of development, there's a thing called Liouville's theorem, which tells you if you have a rational function, it tells you what possible things can be in the result, logs of the things that appear in the integrand, things like that. Then there was a thing called Risch's algorithm, which came along, which said, oh, you can extend that to algebraic functions. And I think in the later versions extended it to trigonometric functions and so on, logs and exponentials and their generalizations. So that was kind of a big deal as a theoretical matter, that you could say, this is the general form of the integral. And Risch's theorem would tell you, if the integral can be done, it must be of this form. And so you must be able to do it by just differentiating that result and matching up the coefficients. Now, there was a small footnote. And the small footnote was, so long as you can solve any algebraic equation. And we've known since Galois in the 1830s that for a quintic and beyond, there is no solution of an algebraic equation in using radicals and so on. You have to go to fancier functions like elliptic functions and so on to be able to solve such equations. And so that was sort of the footnote to Richard's algorithm that makes it not quite so practical. And in fact, we make rather little use of that in our symbolic integration technology today. But in any case, that was an important sort of moment. I think that was in the 60s, late 60s, that that was something where people thought, oh, we're really making progress in computer algebra. Now, there were a number of other things, like factoring polynomials was another area where how do you factor a polynomial? Well, if the basic scheme is you imagine that the polynomial, which involves x's, you imagine that the x is really a number modulo some prime. And then what you do, or some prime or prime power, I think. And what you do is you say, if you just can substitute in, if that number was just had k possible values, then the polynomial could be factored in this way. And you can deduce that just by looking at the factors of numbers. And what you do is basically, there's a thing called Burley-Camp's algorithm. You do this thing, I haven't thought about this in a long time, there's a thing called the Hensel-Lifting lemma, which basically tells you if you can, you do these, you figure out how does the polynomial get factored with over these finite fields with modular arithmetic. And you do that for mod 2, mod 3, mod 6, mod whatever, and you keep doing it for bigger and bigger moduli. And then there's this theorem that says there'll come a point where you've got the final answer, where you've got the result over the integers, not over modular integers. And there's a finite stack that you need to go to get to the point where you have solved that. So, okay. So that was another algorithm that was, I guess, from the 70s, I think. That was another sort of significant computer algebra algorithm that I certainly used in SMP and so on. Another area that's of great interest is solving algebraic equations. And one of the things that have been proved in the so there was this whole question, given an equation, x cubed plus y squared equals 7, something like this, how can you characterize the solution to that equation? Well, the field of algebraic geometry is all about saying, what does the solution set look like? Is it a bunch of points? Are there lines? Are there these complicated algebraic varieties? What does it look like? And so there's that whole field of algebraic geometry that developed in the early part of the 20th century in mathematics. And that had led to the question, when you thought about these things computationally, was there an algorithmic procedure for generating solutions to arbitrary algebraic equations? Okay, so Hilbert back in 1900 had asked the question, if you look at Diophantine equations where the x's and y's have to be integers, could you make a decision procedure for figuring out whether even a solution, whether even an equation stated in terms of x and y's, in terms of integers, even had a solution? And people tried very hard to figure that out, and a bunch of different classes of Diophantine equations were studied and so on. And it was finally proved in 1968 by my friend Yuri Matiasevich, with big contributions from Martin Davis and Julia Robinson, that in fact, no, it is theoretically impossible to determine whether an arbitrary Diophantine equation has a solution in integers. So you might say, well, I'm going to just try a bunch of integers, but you might have to keep trying it forever. It's something which is equivalent to the halting problem for Turing machines and so on. Will the thing ever halt? Will you ever be able to find a solution? It's something that is algorithmically undecidable. So then the question had arisen about equations over the reals and complexes, where these variables x and y and so on are just real or complex numbers. And Alfred Tarski had shown in the 40s, I guess, had produced a decision procedure which would solve any algebraic equation. So over the reals and complexes and so on. It's a procedure that will gradually grind things around and show you how to get the actual answer for that system of algebraic equations. Also includes inequalities and so on as well. But that was a theoretical procedure. And for many, many, many years, people didn't know how to turn that into a practical way of solving equations. We finally managed to do that. When was it? Maybe starting 20 years ago. And we finally have a practical version of Tarski's decision procedure that allows us to solve arbitrary equations, algebraic equations, and now we've continued that. And sort of the big story of computer algebra ends up being what's decidable, what's not. For example, the question, you've got some complicated expression involving square roots and cube roots and things. Is that equal to 0? Well, that's in principle decidable, but as soon as you have trigonometric functions in there, nope, not decidable. There can be an arbitrary length computation that you need to figure out whether the thing's equal to 0 or not. And so there's a lot of issues about how do you deal with things when there is undecidability like that. And there are a lot of techniques that we've developed in the last couple of decades for essentially using approximate arithmetic with careful kind of control of errors to be able to know what can be true and what's not true, kind of shortcutting the process of actually doing the transformations to work out what can be proved from what, so to speak. But that's been, and so that's sort of one big thing. The other big thing is equivalence of expressions is a big issue in computer algebra. Are these two things that are stated differently actually equal? And in general, that's an undecidable problem, but one needs to do sort of junior versions of that for many, many kinds of things, whether it's for doing symbolic integrals and getting results that humans will understand, et cetera, et cetera, et cetera. I mean, I should say that in the area of symbolic integrals, the way we do them mostly now, and we're actually just in the middle of a multi-year effort to sort of retool what we're doing with symbolic integrals, but the techniques that we've used for a long time are techniques that use fancy mathematical special functions. What happened, back in antiquity, there were, people were doing plus and times and a little bit of powers and square roots and things like that. It wasn't too long after that sines and cosines were invented, that trigonometry was invented. The trigonometry really, I would say, was used by the Egyptians and so on, it was sort of got really organized in the work of Regiomontanus in 1400-ish time frame, who was sort of summarizing astronomy and really cleaning up the notation of trigonometry. But by that point, things like sines and cosines as other functions you might care about existed, along with things like haversines and secants and other things that are not quite as popular today. But by the 1700s, after calculus was invented, sort of one of the questions was, so the reason algebraic numbers like square root of 2 or square root of 2 plus square root of 3 or whatever else, the reason those things existed in a sense was because they were the solutions of polynomial equations. Well, by the time people knew about calculus, they were looking at differential equations. And then the question was, what were the characteristic solutions to differential equations? And so the idea there was that a number of people would find there's this differential equation and it shows up in a bunch of different places. It's useful to think about a new kind of function that we just say is a solution to one of these differential equations. So for example, one of those functions is Bessel functions. There are different kinds, but things called Bessel functions, they originally showed up in Bessel's theory of the motion of the moon, but they also turn out to be the functions that you need to describe the motion of a drumhead, a circular drumhead, and they also show up in lots and lots of other places. And so what typically happened with differential equations is that there were this sort of zoo of special functions that would show up in one equation and people would study them a bunch there, and then that same kind of equation will be showing up, or some transformed version would show up in a different place. And there are now a couple of hundred of these named special functions, which we have provided, I would say, by far the world's finest implementation of in our Wolfram language system. It's been one of the things that we've been sort of, we're I would say, collectors and curators, and it's a lot of algorithmic work to actually implement one of these special functions. But there are whole classes of special functions that are associated with so-called hypergeometric functions, and many, those are pretty general functions discussed a lot by Gauss, whose special cases correspond to many of the special functions that show up as solutions of differential equations. But in the tradition of doing algebra, one of the things that happened is people would have these books of tables, so particularly books of integrals. And there's a famous one, I think it's American, named by a chap called Dwight. But then the thing that happened was there was particularly a tradition in the Soviet Union of doing elaborate mathematical calculation using sort of sophisticated integrals and so on. And so there became quite a tradition of creating integral tables that was done in the Soviet Union. In particular, the famous book of tables was by Gradstein and Rizek. I believe that Gradstein and Rizek never actually met, but nevertheless, their names are on this book of tables together. It was sort of a big, thick, definitive book of tables that existed when I was doing particle physics in the late 1970s and so on. And you would look, was your integral in Gradstein-Rizek? I would say that the methods used by Gradstein and Rizek to do those integrals, I think behind the scenes, they were using a bunch of methods that were based on hypergeometric functions and Mayer-G functions, because those are the sort of typical way that you can do an integral is you turn the integrand into some product of Mayer-G functions, and there's just a big industrial formula that tells you what the integral of any product of some number of Mayer-G functions is. But then the real problem is, can you take this mess of Mayer-G functions that you just derived and turn it into something that a human would recognize in terms of, I don't know, Bessel functions and sines and cosines and so on. But in any case, that tradition actually continued to oh gosh, who are the authors? Another group of three, one of whom is Oleg Marichev, that became sort of the next biggest ever book of integral tables produced in the Soviet Union. And that was sort of the end of the line for that kind of technology. And in fact, Oleg Marichev has worked at our company since probably 1990 or so now, helping us to sort of transfer the technology from that long tradition of Russian integral table making and so on to modern times. And Oleg's sort of, I would say, secret weapon has been all these ornate mathematical functions, like the Mayer-G functions, the Appel F1 function, the Fox H function, all these kinds of things. Each one has its own kind of characteristic world unto itself. And each one, once you can turn an integral into something which lives in that world, then you can make use of all the things that have been discovered in that world to compute the integral. So that's kind of and I would say that in the world of computer algebra in general, sort of one question is, can you get the answer? Another question is, can you get the answer in a form that any human will appreciate? And that's sort of a different and complicated issue. It relates also to automated theorem proving. You might be able to prove a theorem automatically, but no human will understand the proof. You might be able to do this integral, but you'll get this giant thing, and no human will understand what that expression means. So that's one of the sort of issues of computer algebra today. I would say another big one is sort of, can you automate a big thing that we spend a lot of time on is meta algorithms, where there may be many different ways to solve Diophantine equations, let's say. Even if you can't do it in general, there might be 30 methods that allow you to solve the first trillion equations with no trouble. And the question is, in any given case, which is the right method to use? And that's a whole bunch of technology we built for doing that. All right, long answer, what I thought would be a short question here. Let's see. Okay, I see is commenting. Boy, it's doing a bit of me history here. There's a paper I wrote called Test for Planar Events in Plus or Minus Annihilation. And apparently in the acknowledgements, it says, we're grateful to R.D. Field, that's Rick Field, and R.P. Feynman, that's Dick Feynman, for the use of their JET development computer program, and to the MATHLAB group of the MIT Lab for Computer Science for the use of MACSYMA. The question from IC was, what was the JET development computer program? Oh boy. Well, let's see. QCD, theory of quarks and gluons, a fine and lovely theory that got a big boost in 1973 when asymptotic freedom was discovered, when it was discovered that the harder you hit quarks and gluons, the less they seem to be bound together. But what happens is when you have a high energy collision, let's say let's say, two protons that are made of quarks glued together with gluons, you have this collision, and maybe two quarks really hit each other, and they get scattered out at very large angles. Okay, but quarks, free quarks, don't exist. And so what happens is the force of attraction due to these gluons gets bigger and bigger the further away these quarks get. And what you get is this kind of, as this sort of string of a different kind than string theory, although somewhat related, develops between a quark and, let's say, an antiquark. It's sort of this tube of gluon energy between these two particles. And as the particles get further and further apart, this tube gets more and more stretched, and eventually it starts breaking up. When it breaks up, it will form sort of quark-antiquark pairs. And instead of just having this one quark that's getting further and further away, you'll have a whole chain of particles produced. And so in a typical high energy particle event today, there might be hundreds of particles produced, pions and kaons and the occasional, hyperon and a bunch of other particles, rho particles, etas, all kinds of things. You produce all these things, which are all various excited states of quark-antiquark pairs or whatever else. The process by which that happens is a process that cannot be well modeled by sort of the approach to QCD that allows one to use Feynman diagrams and so on, because that approach relies on the interaction strength being quite small. But in the place where all these particles are being produced, the effective interaction strength is large. So there's this process of what one might call hadronization that happens. And that process will turn what was just a quark or a gluon that was zipping out from a particle interaction, it will turn it into a bunch of hadrons, a bunch of ordinary pions and protons and things like that, by virtue of just sort of plucking by plucking, like, say, quark-antiquark pairs out of the vacuum and things like this. So this process of hadronization, there's a question of, and that produces this jet of particles in a certain direction. So at the time, and this was 1978 or so, there was a lot of interest in, well, could we see the sort of signature of quarks and gluons in these jets going out in different directions, jets of particles going in different directions. Now, we're 40-something years later, that's been turned into quite a fine art of studying jets and so on. And yes, it really is true that the core of a jet is a quark or a gluon. And so, but at the time, there was a sort of question of how would you model the sort of formation of jets, knowing that standard kind of the sort of perturbation theory, as it was called, of QCD, where you're just saying there's one gluon exchange or two gluons exchanged or whatever, that wouldn't work. You're dealing with these giant tubes of gluons with sort of infinite numbers of gluons being exchanged. So you needed a sort of phenomenological model that said how many particles would get produced and which particles would get produced with what energies and so on. And so that was a program that, I think Rick Field, Jeffrey Fox worked on a Fortran program that was for this hadronization process. And I guess I contributed a bunch of stuff to it, and Dick Feynman contributed stuff to it. Sort of the goal was to have a sort of approximate model for how hadrons will be formed in these jets. And I don't think I wrote very much code for it, even though I knew perfectly well how to write code. And to my somewhat eternal shame, I did not work on the design of this, on the sort of functional design of this program. I think by the time we were doing this, by the time the big version of that was being done, I was already working on SMP. So I really knew a whole bunch about language design, but I really wasn't paying so much attention to this QCD particle physics type stuff. And I say long time shame because that program that we wrote, primarily Rick Field, I think, wrote, that program sort of grandfathered its way through, I think, to the modern jet development programs. And that program could have had much better design. I mean, the way that you specify, a 13 is a pi plus, a 14 is a pi minus. So I'm making those numbers up, but it's the way of specifying sort of what is the structure of a jet, what's its particle content, how do you define all these different pieces in modern times? And maybe I should do this as an exercise sometime. There's I'm sure, a very beautiful symbolic design that can be given for that, which at the time, by 1979 or so, I understood that stuff fairly well. I should have been able to give and didn't give. So that's probably led to more grotesque code in particle physics than should have been there. I'm sorry, I was doing something different at the time. Let's see. Questions here. Oh boy. All right, I'll try and take a few other questions here. Question. There's a question from Mikhail. What was the main thing that I learned working with Dick Feynman? Oh, I don't know. You know, I think, as he would put it, you know, he was very big on the damn the torpedoes, full speed ahead. That was his phrase for, you know, just because you don't completely know how to solve some problem doesn't mean you shouldn't try and do it. And I think that was the thing that he would just like, okay, there's some particular problem to solve. Let's see what we can do in solving it. And just because nobody's solved it before, and just because whatever, it doesn't really matter. You know, one can just sort of use the techniques one knows and try and figure things out. I mean, he was also, I would say, very down on the idea of, well, there are experts in this or that area, and you just ask them what the answer is. I think his experience, and sometimes mine too, is that you ask the experts and they tell you something unbelievably complicated. And A, you don't understand what they're talking about. And B, when you actually, if you actually do understand, you realize they missed the point. And the most common reason that happens is that some field has developed, and at some point there were foundational issues, but then, you know, 8 academic generations later, nobody thinks about those foundational issues. They're just dealing with the leaves of the tree that have developed many years later. And that means that often when you ask about some question, what you'll get is an answer involving the leaves of the tree somewhere up here, and you don't, and that answer really won't address the fundamental issues that you're trying to deal with. So I mean, I think Dick Feynman was very big on the figure everything out for yourself, and very down on the read what other people have done. I tend to prefer to do my homework better, although it's sometimes quite challenging. I think that you know, I do think Feynman always liked exposition and trying to explain things to people. And I suppose implicitly, I don't know whether that was how come I got on fairly well with him or what. But I mean, I've certainly, as you can kind of tell from my efforts here, I'm certainly also into this kind of exposition thing. I mean, I have to say that I had not forgotten, Dick Feynman had this thing he called Physics X, which was kind of a pseudo class for, I think, undergraduates at Caltech, where he would like answer random physics questions. And he forbade anybody like me ever showing up to one of those things. It was only for the you know, for the undergraduate crowd. Now we have live streaming, so it's a different story. But I suppose that my efforts in doing science and technology Q&A, I had not forgotten Dick Feynman's Physics X in thinking about those kinds of things. And I think, I mean, I certainly always liked to I always liked to see kind of his efforts at exposition, and somehow the way that he would would try and take ideas and boil them down to something as simple as possible. I mean, I suppose, okay, you asked me, what did I learn? I suppose that this idea that ideas can be boiled down is probably, that's not something when you learn physics from textbooks, even when you do physics research, it's not an obvious thing to know that sort of any idea can be boiled and boiled and boiled until it is really at its essence and as simple as possible. And he was very big on that. I've been very big on that. That's sort of an essential feature of this language design process that I've spent so many years on. It's also something which, in the end, with like our theory of physics these days, was a necessary kind of attribute or approach to take. All right, a couple more questions here. I see David asking, have you attended any ICMs, International Congress of Mathematicians? Oh no, wait a minute, he's saying ICMPs. No, I have not. I thought it was asking about, I've never even heard of those. The ICM, the International Congress of Mathematicians, is a sort of famous collection of the world's mathematicians held every 4 years. And like Hilbert's address in 1900, where he presented his 23 problems, was at an ICM. I personally, just for fun, have collected the proceedings of most of the ICMs up to the present day. It's really interesting to look at some of the older ones, and they're very they have certain they're very international presented, as in they have very they list off the countries. Some of the countries don't exist anymore, and who all the delegates from each country were. And rather charmingly, they also list the particular hotel address that each one was staying at, printed for posterity in these books. And I was just recently actually looking at the 1912. Okay, this is a little footnote to history point. I was looking at the 1912 ICM proceedings just a few days ago, because it turns out that the idea of game trees, so when you play a game, chess, tic-tac-toe, whatever, given a particular position of the board, there are multiple possible things that you can do next, typically. And you can imagine making a graph of sort of, given the state of the board now, what can that lead to next? What can that lead to next? And so on. And then on all those different sort of paths in the graph, some of them will lead to black wins, so others will lead to white wins, and so on. Well, so the question was, when did people first start creating these kinds of graphs to represent games or game trees, that if you don't deal with equivalence between different paths, it's just a tree of possibilities? When did people first start talking about those? And the answer is, first person who sort of formally wrote that down mathematically was Ernst Zermelo and talked about it actually in the 1912 ICM. And it's kind of charming. It's a paper called On the Set Theory of Games. Zermelo was most famous for ZFC, Zermelo-Fraenkel set theory, which was an axiomatic basis used, well, people at least say they use it a lot today as sort of a foundation for mathematics and set theory. But Zermelo was also trying to take the set theory franchise, so to speak, and apply it to other things. And in this like 4-page paper or something, he applies it to this idea of games and game graphs and game trees. He doesn't actually draw a graph. He doesn't mention the word graph. Graph theory wasn't a big thing at that time, although Euler had talked about it earlier. But it was, he kind of presented the sort of first example of a game, the concepts of a game graph. Although at the time, I think there was sort of, the idea was somewhat in the air, because there had been a lot of analysis of chess openings, chess chess closing situations and so on, chess problems. And so there had been discussion by some of the sort of chess aficionados, the most sophisticated chess playing people, about whether there was sort of a mathematicization of chess openings and so on. And that, I think, directly fed into Zermelo's work. So the answer, so I personally attended ICMs? Yes, I've been to a few of them. I went to the one in Kyoto in, I don't know, when was that? Must have been 1990, perhaps. And then long hiatus, I went to the one in Seoul, Korea, about 6 years ago, and I went to the one in Rio de Janeiro in, when was that? That was a couple of years ago, 2-3 years ago. I have to tell you the sort of just a funny story from the ICM in 1990, I guess, in Kyoto. It was a time when Mathematica was very young. They'd just come out in mid-1988. And we had a trade show booth there. And there were trade show booths from publishers and things like this, but not really from software. We also had this poster that we had made for the ICM. And it was a poster of the zeta function. And it was the Riemann zeta function, which is this function that characterizes the distribution of prime numbers. And there's this Riemann hypothesis that says that the zeros of the zeta function have to lie on this critical line. If you plot the zeta function, you find that it wiggles like crazy. And so it's sort of not surprising that the Riemann hypothesis has been hard to prove since 1859 or whatever it was. And so in any case, we made this big poster of the zeta function, and it was plotted out, showing all its wiggles and so on, and a bunch of information about the history of the zeta function and Alan Turing's mechanical computer design for computing the zeta function and all kinds of other history there. Okay, so we're giving these out at our trade show booth, and some mathematician comes up and says, "Can I have like several of these posters?" It's like, "Why?" He says, "Well, I want to cut them up." Why? He says, "Well, I studied the Riemann zeta function, and I'm working out things about the integrals of the zeta function, and my plan is to take this curve that you've so nicely drawn and to measure integrals by cutting it up and measuring and weighing the pieces of paper that you get from these different integrals of the zeta function." And I happened to be talking to I sort of heard this conversation, and I was like, "That's just crazy. Why do you think we are giving away these posters here?" It is because we have a software system that will compute this poster. You could just use that to work out these integrals. Now, to the credit of that particular individual, after an initial, "Oh, I don't use computers," and so on, I did get him to sit down and look at it, and he went away very happy. And I think has been a long-time user of our software system, probably ever since. And I know did some interesting number theory with it. So that was a sort of a story with a happy ending, but I think that was a moment of transition from the mathematicians who don't believe that computers could possibly be useful for anything, and the only way you can do integrals is by sort of estimate integrals is by cutting posters out of paper, to the present time. That was sort of a watershed moment as far as I'm concerned. All right, let's see. Maybe one more. Let's see, I see a question here about the history of the university system in the US. I don't know this in complete detail, but I can say a little bit about that. I mean, the question of history of universities overall, and when did universities originate? What is a university? I mean, to some extent, Plato's Academy, which lasted for what, 400 or 500 years, was sort of a university-like thing, complete with the groves of academe type concept. But I think this concept of kind of lecturers and students and so on, that's existed for an awfully long time. In the 1200s, that was the time when the earliest sort of modern-ish universities came into existence in Bologna, in Oxford, in Paris. I don't know fully the history of that. I know of having grown up in Oxford and seeing these old colleges, like New College, the second oldest college, one of those naming mistakes perhaps. But one feature of colleges is you look at them and they've got these walls and they've got ramparts and they've got serious, Middle Ages protection, so to speak. And so you kind of realize from that being being in the professor class wasn't necessarily, not everybody was going to be like, "Oh, how cool, there are professors here." I think there was a regular phenomenon of people upsetting the locals by thinking about something futuristic and maybe good idea, maybe bad idea, I don't know, and getting sort of attacked or pushed out of some place or another. And I think that's how several different sort of universities started growing up, was people were pushed out of town X, and so they went to town Y, and so on. But the kind of this idea of the university originated, I think, at that time, and I think a lot of the at the time, theology was kind of the principal kind of intellectual pursuit. And I would say that the principal kind of place where people who were educated went was into sort of applications of theology and into being, various kinds of, priests and bishops and who knows what else. That was sort of where it was a core intellectual activity. I mean, I think subsequently, law, later, I think medicine, but I think they were much later. Those were much later kinds of things. And also when people studied, a lot of what they were studying was Aristotle. They were studying it's like if it isn't an Aristotle, it isn't real type thing. And obviously by the time of Copernicus and later Galileo and so on, one was beginning to see sort of a breaking into kind of new areas of science. And obviously the Renaissance and such like led to all kinds of sort of explosion of new knowledge that wasn't in Aristotle type thing, and wasn't in the Bible and so on. But but universities started up when it was Aristotle and the Bible, and Euclid, I think that was kind of the original model. And I do find it amusing that universities, which often tout themselves as we're for the future, we're doing everything new and cool, and we don't believe in history and all this kind of stuff. I'm not sure I agree with all of that, but in any case, I do find it amusing that when they do things like degree ceremonies, people are still wearing gowns and mortarboards, and sometimes they have things in Latin and so on. And it's like, well, if you want to look serious, you have to show those long roots back to the 1200s. Even if you don't believe in history, even if you don't teach history today, you're using that as the credibility for the enterprise today. But in any case, the universities, my impression is sort of even, I don't know in different countries, but in England, for example, universities and the church were deeply interwoven for a long time. And it was often, I think even when, even in the 50s and 60s, it was finally starting to be the case that you could be a fellow of some college without being declared as, a Church of England, whatever it was. So I think, that was the thing that connection lasted a very, very long time. But universities, as in the UK, where I kind of know a little bit more of the history, Oxford and Cambridge were the sort of principal universities. They were broken into these few tens of colleges, each of which had their own separate endowments. They owned land in different places, et cetera, et cetera, et cetera. And they also had their own fellowship of people paid for by the college. And but there was sort of a confederation of these colleges that made up the university. Well, the sort of a watershed time for universities in the UK and the US was the Second World War, when I would say, well, a number of things that happened. First of all, big influx of students, after the end of the war, and also, well, I'm trying to think what all the dynamics were. I mean, I would say, by the way, in the US, that the story of universities was, the universities in the US were not yet thought to be sort of distinguished on a global scale until, I would say, solidly into the 1930s, 1940s. It was very much of, let's get professors from Europe. That was the source of all professors, so to speak. There were professors from Germany, professors, fleeing the Nazis and so on. Lots came to the US. Then there was a wave from the UK. There was the so-called brain drain of professors sort of minted in the UK. That was much later. That was 1960s and so on, coming to the US. But I would say that in the early part of the 20th century, a serious professor in the US tended to be a European educated person. Now, there were exceptions to that, and there were a few kind of increasingly, even people like Norbert Wiener, who was seen as one of sort of a quintessential American story professor, sort of the patron saint of MIT in some ways. he had gone to Europe for some key part of his education, and that was a fairly typical thing at the time. It was it's funny how history moves on, and now coming to the US for some part of sort of university education is seen as sort of the global thing to do. But at that time, it was sort of Europe was the top place. I think what happened in, and I don't know whether it was the end of the Second World War or whether it was I think this whole military-industrial complex that had come out of World War II was a thing that drove a more systematic approach to universities. I mean, during World War II in the US, many universities had done a lot of support for the war effort, and lots of things like the Research Laboratory of Electronics, let's say at MIT, or there's a long list of different kind of facilities that were created at universities during World War II to support the war effort. I think the thing that happened as a result of that was the intermixing of government support of universities with the primary teaching type mission. I think that was the time when universities really started to get large amounts of government funding, direct government funding by grants, as opposed to funding by loans to students, which is another thing that developed somewhat later. But I think then that the thing that developed at that time was this idea that there is government funding for universities, and there are these, and that's what happened in the US. In the UK, one of the things that happened was that there started to be departments of X, Y, and Z. It had been, there are just these colleges, and the colleges have fellows, and the fellows, teach, and the fellows will sort of, the philosophy professors, dons, as they're called in Oxford, for example, will like get together every so often, but there isn't a department which is sort of an organized university-wide thing. That came into existence certainly by the 1960s, and I think it was happening also in the 50s. And that sort of changed the character of things by making everything much more streamlined, and much more, there is a definite curriculum, there are these definite departments. It's like you're not just a fellow of a college working, thinking great thoughts. You are in the physics department, or you're in this department or that department. So that became, as the enterprise got bigger, that became something that was much more streamlined. I think in the US, one of the things that happened was, for example, the notion of tenure came in, the idea of, I think that was don't really know how that related. I think there was this, what was it, American Association of University Professors or something. I think that was the thing that caused that to be created. I don't really know the history of that, but that happened by the 50s. So that was another dynamic. Another dynamic that affected universities was the creation of textbooks. I mean, it had been the case that, if you wanted to hear Professor so-and-so, you would have to go to that university and hear Professor so-and-so. In the 1950s, publishing companies, I think Addison Wesley was the first one to really do this seriously. They basically said, okay, Professor so-and-so, I think it started at MIT, actually, that particular one. You've got these wonderful lecture notes. Let us turn these into a book and publish it and have students buy the book. While that wasn't unheard of in other places, that became sort of a streamlined process of the kind of textbooks as a driving force and a thing that students were expected to buy. I think in US universities, there's the whole sort of formation of departments and so on. I think the period of time when there was huge expansion in that was post-Sputnik, after 1957, and after was kind of a big, oh my gosh, the Soviet Union is taking the lead in space and in technology, we better catch up. And there was a big effort, and one of the big sort of beneficiaries of that effort was universities, and sort of a much larger amount of government funding to universities for doing basic research. The question of how universities have evolved with respect to all their different, the concept of majors and the concept, the streamlining of classes and all that kind of thing. I learned just recently that Andrew Carnegie was responsible for the notion of transferable credits between universities. When he was funding a bunch of universities, he basically made it a condition of his funding that they have somehow transferable course credits between these universities. He had some kind of system for standardizing those kinds of things. I think that the kind of the history more recently is there's this sort of tension between students as customers, government as customer, university professors as people who want to do a particular kind of thing, people donating money to universities wanting to do different kinds of things. I mean, obviously that's a dynamic I don't really understand the history of, because I think it relates to the tax deduction status of giving money to universities, which is a very characteristically US type phenomenon, something you don't see in other countries, at least in quite the same way. And that's been an important contributor to the sort of growth of universities. But I don't really know the evolution of sort of what universities have done and what departments even exist at universities. It's a big challenge for a university. How do you create a new thing? What new things can come into existence? We've got a department of X, a department of Y. I remember when departments of computer science were first coming into existence. This was in the 1980s. There were plenty of universities which didn't have a department of computer science. I think Harvard didn't have a department of computer science. Princeton didn't. Sometimes they grew out of an electrical engineering department. Sometimes they grew out of a business school. Sometimes, very rarely, they would grow out of something like a math department. But that was a sort of creation of a new department. Molecular biology was another big one that got created. For a while, universities would have linguistics departments. That was a thing that got created for a while. For a while, they would have geography departments. It's sort of interesting to see the growth of some of these departments and their decay. Applied mathematics is another one which got created. Some of those in the aftermath of World War II, applied mathematics departments got created, which may or may not have survived in that case, because it became a little bit unclear. What do you mean by applied mathematics? I think in geography, it's sort of like, what do you mean by geography type thing? But so some of these departments came into existence and disappeared. The sort of creation of new departments has been pretty challenging. I mean, some universities, I know University of Chicago, for example, had a concept of these committee on X, like one of the famous ones was committee on social thought, committee on theoretical biology. These were things which were sort of proto-departments that were created. I'm not sure whether they had a fixed time period or not, but there was sort of an interesting example of a kind of a special projects-like approach at universities of how do you have a department that isn't yet a department, so to speak. So anyway, I think in the present time, obviously, there's lots of question about what should universities be doing and what are the different forces at work on them. I have to say that I think one of the things that was a mission of the universities from the 1200s on was just the generation to generation preservation of knowledge, which is a pretty good idea. I mean, one might think all knowledge is just passed down by books in today's world. I don't think that's really true. I think that the kind of the person-to-person transmission of knowledge and transmission of sort of the what's important about knowledge and how to think about things and so on, I do think there's a role for sort of the human transmission chain of that. And that's something that universities had signed up for in the 1200s. And it will be a big shame if that finally disappears in the 21st century. Hopefully it will not. I think that it's the idea that, and I should finish off in a moment here, but the idea, universities had this mission of, passing down knowledge from generation to generation and teaching the next generation this or that. The separate mission of let's do new research had been kind of a sideshow that was done by a few crazy professors back in the day. And as there started to be lots of government funding for universities, became a thing that was part of what the university did for a living. And precisely what the correct sort of connection between sort of doing basic research and the education mission is not completely clear. I mean, to some extent, it's like, well, if somebody's going to educate the best, they should be at the leading edge doing the fanciest research. Sometimes that's true, sometimes it's nonsense. Sometimes the person doing the fanciest research can't communicate it at all. And sometimes the person who is just really spent a lifetime honing their teaching skills is much better able to communicate things, even things which are right at the leading edge. And so it's a complicated sort of interplay between those two things. I think the US is in the US, the majority of basic research is done at universities. There are government labs that are very good, but they're smaller than the university enterprise. In other countries, I don't know why Japan comes to mind, for instance, a lot of the sort of the leading edge research is done in industrial research labs rather than in universities. And I think there are different countries. France, for example, has an elaborate government funding mechanism, so does Germany, for research happening, like Germany, the Max Planck Institutes are sort of quasi-university entities that are really government places where research gets done. And so this weaving in the US of universities with research is something particular. And of course, not true of all universities. There are the research universities and the liberal arts colleges. There are other universities, and they have somewhat different missions, but the kind of concept of the research university, I think, is a particularly American construct at this time. All right, I should probably wrap up now. Thank you for those interesting questions, and I see that we have plenty more for next time that I didn't have a chance to get to this time. And I don't know, answering these questions, somehow I was having these terrible allergies from having been outside here on my sort of on this island, and somehow answering these questions has made my allergies go away. So that's thanks for that too. All right, and as a matter of fact, I have another live stream software design meeting coming up in a few minutes. So thanks for joining us here. And you know, I have to give one little commercial, one little promo thing. We happen to be at our company in an expansionary phase right now and have a bunch of very interesting job openings. And if you're interested in any such things, including things that are like talent and interest, but not necessarily specific knowledge, please do check out our opportunities page. All right, well, I'm disappearing for now.